In our last week, we learned about something called impedance, where certain elements of a circuit are going to react and basically act as resistors, even though they might be capacitors or inductors. So, just to remind you, this was called XC and XL, the impedances, the impedance formulas. The impedance of a capacitor was 1 over 2 pi frequency times capacitance, and the impedance of an inductor is 2 pi frequency times the henries. Okay, so we're going to be setting up a situation where we have some sort of AC current, and we have a resistor, a capacitor, and an inductor in series. So they're going to be R, C, and L. But really, it's not going to matter so much which order they are in. It doesn't matter, actually. We're going to have to figure out a formula that whenever we encounter an RLC circuit, we just want to know the overall impedance and also what's called the phase angle. In our phase diagram, what we see here is that we have a normal VR. A resistor is in sync with the current, and then, as we've talked about before, this is our voltage of a capacitor and the voltage of an inductor. Now, the thing is that if you add up all of these voltages together in our phasor diagram, that will actually give you the true voltage of what you'll see in the circuit. So we'll call that V total. And also, this angle between what is normal and what our actual voltage would be, it's called the phase angle, and that's how much it is off from what we would expect without any impedance like this. Alright, so what we have to do is figure out, using these vectors, figure out what V total is. Now the first thing we need to know is, sorry, this is a C here. If that doesn't look like a C, that's a C right there. We need to find somehow the magnitude of this total vector. And the magnitude of that is, well, we have to combine VR, VL, and VC. One trick here is that if we add VL and VC, if you add two vectors going in opposite directions, like this, you're basically going to be canceling each other out. And if the red one is larger, your total vector overall is going to be in direction of whichever vector is bigger. And so let's just say, for simplicity, that L is bigger. And so when you add VL and VC together, you're going to get this vector right here. And we would denote this as VL minus VC. So we're basically assuming that L is bigger than C, and that green vector represents our distance. Now, to figure out the magnitude over V total, we're actually going to be using the Pythagorean theorem. Because if I just slid this vector over, I would have a right angle, and I have to take the length of our resistor vector plus the other vector after you square both, and that's just going to be Pythagorean theorem. So let's start doing that. V total squared C squared equals A squared plus B squared. Okay. And now what you're going to be doing every time here, if you have to kind of redo these formulas, is we need to rewrite this not in terms of voltages, but in terms of current and impedance. So here are some things to remember. VC is going to be the same as I times the impedance of the capacitor. Now we wrote it where it was like V over X because we were relating it to resistors, but this is more helpful here because we can just take this and plug it in right there. VI for the inductor is going to be the same thing. I'm sorry, VL. So this should be VL right there. And then the V for the R, VR is going to be just I times R. And that's always been the same. Okay, so let's rewrite this. And then in here, we're going to have to substitute now I realize my C's and L's look very similar, so I'm trying to keep them clear here. Alright, now we have a little algebra to do here. So, this is going to be basically I squared R squared. You'll notice that there is an I that could be factored out, and then it can be taken out if you keep it squared, so it's going to be I squared, and then left over is going to be xc minus xl squared. Okay, now we can actually factor out the I squared so that it's v total I squared, and then in parentheses R squared minus plus xc minus xl squared. Alright, so this is pretty ugly, but we get to square root everything. And if we square root everything, v total is going to be the current times the square root of this right here. Alright, now this equation right here that I'm highlighting, sometimes it's just written as Z, the impedance in total. And for an RCL circuit, this is what you would use every single time. The thing is, in other circuits like LR circuits or CR circuits, you're going to have to calculate a different one, because if you take L or C out, you don't use that impedance. So this is for RLC circuits. The other thing we need to find here is theta, the angle that this vector makes. And so just remember here, and I'll do this in red on the side here, the tangent of theta of this right triangle here, so opposite over adjacent, the opposite side is this green stuff here. So you have VL minus VC, and then you have VR on the bottom, which is your adjacent side of the triangle. Okay, and we want to do the same thing that we did before. We want to substitute so that we're dealing with currents and impedance. So VL is IXL minus IXC all over IR. Now you notice I have I in every one of these terms. These will cancel out, and I just have tangent of theta equals XL minus XC all over R. So to find your angle, this is what you would use in an RLC circuit. So let's do an example here where we actually use some numbers here. Alright, so example. We have a lot of numbers to plug in here. Let's say we had a 448 ohm resistor. We had a 1.5 microfarad capacitor, and then we had 35.7 millihenry inductor. We plug this all into an AC circuit. It has 35 volts, and then the frequency is 512 hertz. Okay. After all of that, we can just go right to these two equations to figure out voltage and theta. So that's what we're going to find first. Total, we want to figure out, we want to find the current, and then we want to find the phase angle. So first thing we need to do is we need to figure out X of the impedance of the inductor and the impedance of the capacitor. So inductor is going to be 2 pi frequency times the henries, the amount of henries. So that will be 2 pi 512 times, and since it's in millihenries, I'm going to write 35.7 times 10 to the negative third. Then before I throw in my calculator, I'm going to set up my capacitor. That's going to be 1 over 2 pi frequencies times capacitance, which would be 1 over 2 pi 512, and then microfarads would be 1.5 times 10 to the negative 6. Alright, I'm going to pause this and I'm going to plug all those numbers in. Okay, and so I calculated the impedance of the inductor is going to be 115 ohms basically. The impedance of the capacitor is going to be 207 ohms. And then we know that the resistor is going to be 148 ohms. So now we have everything to go right to the impedance. Now, the impedance is Z, and that will be the square root of R squared plus the difference between the impedance of the inductor and the capacitor squared, all that square rooted. So when I plug this in, it's going to be okay, working that all out, I get a total of an impedance of 174 ohms. Now, we're going to just assume that the information here is root mean square. And basically, functionally, whenever I see examples of this, it's pretty much you could just exchange them, unless it's specifically talking about the difference between root mean square and the amplitude of the wave. But anyway, what I'm getting at is that we have voltage equals current times the impedance. So we're going to have a voltage of, and in this problem we have 35 volts. We want to know the current, and we know the impedance is 174. If we divide both sides by 174, I'm getting 0.201, or about 200 milliamps. Okay, now that is the total current in the circuit. If we want to know the phase angle, we have to do the tan inverse of this stuff. But we've already calculated all that. So this is going to be 115 minus 207. And then downstairs we have 148. When I plug this into my calculator, I get negative 32 degrees. So if you were to think about the phase diagram, you have the R going this way, VR. You have VL, and you have VC. Now, because our angle is negative 32 degrees, we actually have the V total that's going to be lagging a little bit, or leading, depending on how you talk about it. But that would be the phasor for the total. And not only that, but the magnitude of this vector is going to be 174.